the third mathematical meeting in memory of Herbert Gross. We begin with a minute silent in memory of Herbert Gross. Please stand up. I give immediately the word to Herbert Gross because her health situation is not ideal and he has to go away as soon as possible.
Ich spreche nicht Englisch, Spanisch.
Wie du willst,
Gut, ich spreche Deutsch, weil die meisten verstehen. Ich bin sehr erfreut und auch berührt, dass ihr wiedergekommen seid, nach 30 Jahren, nach Herbertsburg zu diesem Treffen. Und ich bin auch sehr erfreut, dass ihr immer noch Freude habt und Lust in dieses schwierige Gebiet, das Herbert eröffnet hat, wiederum einzutauchen und dass ihr ja schon eingetaucht seid, ganz am Anfang mit der Dissertation. Ich danke euch, dass ihr gekommen seid. Ein ganz großer Dank geht an Remo, der schon vor einem Jahr begonnen hat mit den Vorbereitungen und der keine Mühe gescheut hat, um dieses Treffen möglich zu machen. Es war diesmal nicht einfach, weil all die Sponsoren waren nicht mehr gewillt, wie früher Geld freizumachen. Es war ein Mathematikertreffen. Die haben alle das Gespenst der Krise vor Augen. Ich danke auch. Aber Remo hat es möglich gemacht. Ich danke auch Aldo, der auch noch geholfen hat am Schluss mit der Realisierung der Atti bei technischen Problemen. Und ich danke Suzu, der sofort gesagt hat zu mir, weil er weiß, wie wichtig mir meine Vergangenheit ist und wie sehr ich mich auf das Treffen mit euch gefreut habe. Er wolle es filmen. Schauen wir dann, wie es herauskommt. Er hat ein bisschen eine komplizierte Apparatur. Was mich anbelangt, ich hätte euch sehr gerne wieder eingeladen zu uns und hätte mich sehr gefreut, wieder zu kochen, so wie das die Tradition ist. Aber es geht diesmal nicht, weil es mir einfach nicht möglich wäre, so lange in der Küche zu stehen, nach dieser misslungenen Operation. Jetzt wünsche ich euch eine spannende Reise in die verschiedenen Gebiete eurer Vorträge und freue mich, euch heute Abend und morgen Mittag wiederzusehen.
Come si fa a scorrere un po' più rapido? I studied Hermitian lattice generated by one element which is even. This means that
the element A, the generator A, is contained in B. The generator A represents a subspace of Hermitian space in the abstract setting, and the element B represents the subspace of all trace value elements. And in general, we know that the whole lattice in general is infinite. This was already proven in a Green Book of 1991. The problem is very difficult to describe the whole lattice. For this reason, we start with some special cases. Each special case is given by some relation, and we hope that in force of the relation we are able to describe the corresponding lattice. So in this case, finally, so 10 years ago I was studying the semi-lattice So I resume. The geometric description starts from a Hermitian space E with subspace F and the subspace of all trace value vectors. So these two subspaces generate in the set of all subspaces of E lattice, sub-lattice, and we assume that with all these elements we compute also the orthogonal subspaces of each subspace. Then the corresponding abstract situation is considers some Hermitian lattice in the sense explained by Anna Cecilia. So F to F corresponds an element A, generator A, and B is in the definition correspond to an operation, constant operation. In general, the free Hermitian lattice generated by A is infinite, so I consider the relation F E star, which correspond to A less or equal. But also with this relation, the corresponding lattice is very, very, very big. Practically infinite. So one tried to look for more constraints. So one constraint was this one. which correspond to delta of V over A of 1 delta of 1 over V less than -2. But even with this condition, the lattice is still very, very big. So 10 years ago I started with the calculation of the semi-lattice. Semi-lattice means that only the operation intersection in the geometric situation and orthogonal. Only these operations are considered. So we forget for the moment the addition, the sum. And one situation is given by this diagram. To that I can show the whole diagram. Here. So this diagram describes the lattice also under more condition, but here we see some crucial elements. Generator A is here. B is over there. Okay. B is over there. A orthogonal is here. And here are some other elements. In particular, there are crucial elements, B orthogonal and D. D is the intersection of B and A orthogonal. These play a very important role. And then there are, here in this situation 1C, there are some quotients, in particular this quotient, and I discovered that this quotient is a prime quotient also in the lattice, not only in the semi-lattice, but also in the lattice. 10 years ago I studied this one, and now studied the same situation, but with also and I discovered first that this quotient, you see, this quotient is a prime quotient, and each prime quotient generates a subdirectly irreducible factor, and when the subdirectly irreducible factor is null, then can be separated. And then I consider the rest, and then I discover, moreover, that this other quotient is also a prime quotient, but I needed more energy to separate the corresponding subdirectly irreducible factor, and the reduction is all explanations about the reduction are contained in step 1 and step 2, page 57. In these 2 pages, I explain practically a way to separate this prime quotient. So these 2 prime quotients, the first and the second, play intuitively spoken a sort of rigid parts of the wool lattice, and are disturbing the drawing of any variants. So the fact that one can separate these 2 prime quotients is very important for the subsequent study of the lattice. Okay, then I was separating this, and I went further to study the consequences. Now I close this and I open the document. Time to find the right place, but I can talk a little bit in the meantime. Then I discover so if you open the document, page 66. You find a diagram, and this diagram describes a sort of overview how could look partially the wool lattice, which is 1000. But of course, since it is potentially infinite, I could not draw all elements. But here in this drawing, I replaced relation between elements with dotted line. The dotted line represent intervals. Intervals, this means subset of the wool lattice. Means a subset. So in this diagram you see normal lines and dotted lines. The normal lines represent the relation between elements, and the dotted lines represent subintervals. So now these diagrams illustrates where well-known part, finite, that we call finite part, because this part can be split in via subdirectly reducible factors. And the dotted part represents an infinity of elements, but you can see the play of both parts. You can see in particular where the infinity of these lattices takes place. So I'm coming soon to the right place, hoping. So if you look at this diagram, you perceive where the finite part is and where the infinite part is. So dotted line represents the infinite part and the other lines represent the finite part. So you get an overview. Now, because the finite part is very well known, what can we do? We can split where the finite part is and where the infinite part is. So dotted line represents the infinite part and the other lines represent the finite. Finite. You see, for example, I illustrated this now because the finite part is take this quotient. What can we do? Define by the index gamma 2. To this index corresponds, for example, I illustrated. You see here about also gamma 2. And the subdirectly reducible factor defined by gamma 2 can be separated, and you find the corresponding factor page 79. You see number 2. Table C. This means subdirectly reducible factor. The number 2 this can be separated. The same occurs for gamma 3, which is here. You see number table gamma 3 gives the factor number 3, page 79. And so on. So, proceeding this way, we can separate all the finite part that we see here by normal line. So it remains the rest. Now the question is, how does look the rest? And so we started the rest, step by step. The first step was explained by Anna. This is a special case of even subspace. Namely, when the subspace is totally isotropic. Why did we study a couple, pair of totally isotropic subspaces? There is a very clear motivation, simple motivation. I will show you on the board immediately. And now I have to come back.
Why did we study cop, pay?
The problem is that in the manipulation of this, I'm not surely mastered the manipulation of these technical things. So, I come back here. Then I explain. When we study our structure, it will appear the radical of f, so geometrically the property is f intersection f orthogonal. In abstract description is A intersection A orthogonal. This is defined by R, small r. But there is also another radical that appears. F the orthogonal also intersecting with F orthogonal is another radical. A the orthogonal intersection A orthogonal. This is defined by R1. So, two totally isotropic subspaces, and of course, this is containing this. Of course, we have R. That's what we call R1. This was the motivation of the study described by Cecilia. So we studied the general situation, and this situation is a little more simple than the case treated by Cecilia, a little more simple. And it gives rise to a structure which is a substructure of our structure we are looking for. The problem is that there are many elements, so the idea is to proceed stepwise. And the first easy situation to study is given by the following relation. A orthogonal equal R1. This is the first simple. And this situation is studied in the second work given in the proceedings. And the corresponding lattice is this. So, right. Here is A. Here is the radical of A. Here is R1, the radical of A orthogonal, in this case. So it is a special case where the orthogonal of A coincides with R1, okay? And in this case, we obtain this special situation, this structure. So, then we make the next step. The idea, the basic idea of the next step is the following. we study our lattice in function of A orthogonal. So in our lattice, there is the element A orthogonal. We know this example, but in general, we have here R1, but in general, A orthogonal is very big. Is here. The idea is to look crucial subintervals of this big interval. So this is the idea. To look for subintervals of this and to study one interval after the other. So very optimistically, but the idea is this. So now I put in evidence in this big interval some subintervals. So the first one would be R1 plus R2. What is R2? R2 is defined give you the page so you can look directly. So all definitions are written page 55. So R2 is the radical of R orthogonal B orthogonal. But thanks to the separation, I was talking in precedence. I was explaining precedence. This orthogonal element coincides with its radical. And its radical is called R3. R2. Yes, R2 is the radical of this, and what I wanted to say, this radical coincides with the orthogonal of R orthogonal B. The next element is R3. What is R3? R3 is the radical of R1 orthogonal B orthogonal. It's not easy to visualize this element. I can make better. Then the next element is R4. Therefore, is very easy. It's better to understand. The R4 is the radical of D, and D is the intersection of A orthogonal with B. This is really a crucial element, in particular by our assumption about finite indices. This index is final. The orthogonal intersected with any place is D. D represents, I remember, plays the role of the subset of place value elements. D and A orthogonal is the orthogonal of our generated element. And R4 is the radical of D. So we have all these sub-elements which subdivided this interval in smaller sub-intervals. We go further. Next element will be the B-orthogonal of D. Then the next element will be A-orthogonal intersection T4 B-orthogonal. What is T4? So go back page 55. 55. T4 is the B-orthogonal of A plus B. So here is D. Any place here is A. E take the sum. B-orthogonal of this intersect with B. So here is any place A plus D, B-orthogonal, intersected with T. This is P4. When one studied this structure, one discovered that this is a crucial element. But to explain to you how I had to transpirate the countable number of shirts before I discovered T4 a orthogonal intersection T4 is the next step is a orthogonal intersection T2 B orthogonal. So T4, of course, T4 B orthogonal. T4 B orthogonal, which is a little greater than what is T2? T2 will coincide T2 B orthogonal will coincide with R4 orthogonal, the orthogonal of this, because of our start reduction that I explained in the beginning of my talk. Remember, I was showing the semi-lattice and I was separating two
to rigid pieces. And thanks to this separation, in the reduction, we obtain this equality. So, of course, this plays a very important role because it is the orthogonal of this radical, which is the radical of D. Any place with here is T2 the orthogonal. Of course, T4 orthogonal is contained in T2 the orthogonal. Here is the intersection with the orthogonal. Here is the intersection with the orthogonals, and then we go further. Now there is A orthogonal T1 B orthogonal. And one more, and this is the last, A orthogonal intersection R2 orthogonal. So, for the moment, all the crucial elements I was considered. Now, it is interesting to observe that this index here, gamma 11, so the numbering, in order to facilitate the reading of all words, I conserve the number of indices which were introduced in 10 years ago. So this were number 13 of you have in your library maybe a copy of the proceeding of 10 years ago. The index of this is 11, and it happens that is equal to this ortho via the axioms explained by Anna Cecilia. One can show that this index is equal to this index. The proof, the details of the proof are contained in the outcomes. So I don't have the time now to enter this detail. It doesn't make sense. This index, gamma 15, is equal to this one, gamma 15. So it is interesting what it means when you separate these two. So I forgot to say that these indices pertains to the final part and are prime indices. So when you separate these indices, this disappears. And so after the separation of these, R3 will coincide to R1, and this element will coincide. Okay? Now, in my work, we are now here. We can suppose that these two elements are different. The problem is now to study this part. And this part is very, very complicated. I discovered that almost all subintervals are potentially infinite. Almost each. My conjecture is that this index is prime, but for the moment I don't yet have a general proof, but my conjecture is this. So if you take away this, remains this subinterval, which let's gamma 17, and this is also gamma 17.
Yes, yes.
This is also gamma 17. But this index is potentially I say potentially because you remember by our assumption this index is finite completely in our assumption. So of course all in between elements, the number of all in between elements will be finite in force of our assumption. But the general quantity of all elements that will appear, in fact, is infinite. This is the point. So there are infinitely many possibilities to choose finite number of elements inside. This is the exact meaning. Was I sufficiently clear?
No.
Okay.
So,
El tiempo.
Huh?
El tiempo.
How much?
Finish.
Okay, then I will pronounce just the last statement. When you look the diagrams from page 69 to 77, 78, all these diagrams will show to you the potentially infinite sequences that will appear at least inside all these subgroups. At least, I say, because maybe there are other modes that I can in the moment see. Okay? Thank you very much. Now we have a pause, and by instruction of the hotel, the coffee pause is under the floor by the entry.
Ground floor.
Ground floor, yes. And then we will. Where is my? We will resume at so it is written here.
Das geht nicht mehr. Da müssen wir sofort weiterfahren. Wir müssen den Kaffee machen, damit wir es später.
Now is what time is now? 3:44. So we are you in accordance if we make the pause later, or we make 5-minute pause in order to permit to go to the toilet?
50 minutes.
15? Then we can make 15 minutes, but we have to interrupt in time because we have to give the time to reduce all these to put in order
Where do we have to leave this room? Where do we have to leave the room?
So the program finished is 17. But 1915 we have to meet for the dinner, and all the infrastructure must be put in order here inside in this system. So we have to give sufficient time to Sun Tzu to split all the instruments. For this reason, I can't make exception to the time translation. So instead you will have 15 minutes less than a program disposition. But I remember tomorrow, 9 o'clock, we will make a workshop with Stan. And he will explain a lot of details that maybe we can understand today. Okay? So, pause. Welcome to the third mathematical meeting in memory of Herbert Gross. We begin with a minute silent in memory of Herbert Gross. Please stand up.